yesterday I started talking about approximation algorithms, and we discussed the travel salesperson problem and the set cover problem. And just as a reminder, because I had questions yesterday after the talk, so the main point of approximation algorithms is that we want to solve NP-hard problems. So all the problems we are talking about are NP-complete. And we can't find the exact solution. So we really aim to find some solution which is close to the optimal solution, but not necessarily is exact optimal. And we want to find provable approximation guarantees. And last time we started discussing the balanced cut problem and the sparsest cut problem. And just as a reminder, so in the sparsest cut problem, we are given a graph G, and our goal is to find a subset S of its vertices so as to minimize the number of edges going outside of the set S, or the edge boundary of the set S, divided by the size of the set S. And so this is this blue portion of this expression. And since the complement of the set S has always size between n/2 and n, we can as well multiply this expression by n/s complement. And so we may change the value of this function by a factor at most 2, and we won't care about constant factors anyway. So it's easier actually to think about this expression and maybe put this n somewhere here. It's just a constant factor. So this is really our goal. So in this way, we want to find a set S, minimize the edge boundary between S and its complement, divided by the number, by the size of S, and divided by the size of the S complement. And in this way, we have an extra bonus that the expression is symmetric with respect to S and S complement. This is our goal. And the problem can be rewritten in terms of cut metrics just equivalently. So just by the definition for a set S, the corresponding cut metric is the following. We define this distance xuv, and xuv is equal, it is defined for all pairs uv, not necessarily edges. So xuv is equal to 1 if u and v lie in different parts of the cut. So if u is in S and v is in the complement, or the other way around. And it is 0 if u and v lie in the same part. Either u and v lie in S, or u and v lie in S complement. And as we seen, this is a metric space or semi-metric space, because we allow some distances to be 0 even if u and v are not equal. Using this notation of cut metrics, the original problem can be rewritten as the minimization problem of sum over all edges distances of xuv. So we sum up all lengths of edges in the graph and divide them by the sum over all pairs uv and distance xuv, because the expression on the top is exactly equal to the number of edges going from S to S complement, and the expression on the bottom is exactly equal to S times S complement. Okay? Any questions so far? Clarifications about the cut metric? And of course, the reason why we do it is that now we want to relax this problem and write a linear program and try to solve it. So the advantage of linear programs, of course, is that this is something we can solve in polynomial time. And in general, it's useful to think about linear programming. When we write a linear program, we really want to find maybe not one solution, but rather some probabilistic distribution of solution. So think of these XUVs, or in general LP variables, as probabilities of some events. So here we also can think of just a variable XUV as some probabilities that U and V are separated. And sort of the optimal solution tells us that there exists such distribution, trivial distribution, where just supported on one basic probabilistic event. So XUV is either always separated or never separated. In this formulation, when we want to minimize this sum and we require that XUV is a cut metric, the problem is exactly equivalent to the original problem. And because of this, it is as hard as the original problem. What we can do, we can relax this condition and require that XUV is just a metric, not necessarily a cut metric. So what we will have, we want to minimize again sum of XUV divided by all pairs and we will have conditions that XUV is non-negative, XUV sort of equals to XVU. So the standard requirements for a metric space and triangle inequality. And this is almost a linear program. So what we need to do, we need to take care of it and convert it maybe to a true linear program. Because so the problem here is that we have here a fraction in the objective function, but this is somehow easy to deal with. So as you can see, this program is homogeneous with respect to variable x. So if you multiply x's by the same number, then the value of the objective function won't change, and all the constraints will be satisfied as well. So if you pick one solution and then multiply all the values by the same number, so if you replace sort of XUV to lambda XUV for any positive lambda, then all these obviously triangle inequalities will hold. It still will be a symmetric distance. We will still have this expression, so all values will be non-negative, and the value of the objective function won't change. So without loss of generality, we can just assume that this expression is equal to 1. And this is the constraint we will add to the LP, and afterwards we can solve this linear program. We could as well use any other number, so 1 is not particularly important, but that's what we will do. So we can solve this program, and now the question what we do next. And our goal is to really convert it to a cut metric, but instead we are fine if we can find the distribution of cut metrics. So if we can express this XUV as a distribution of cut metrics, then so we will be able to find the solution, and that's what we are going to do now. So we will look at metric spaces that can be expressed as some combination, let's say, lambda s, x sub s, UV. So here X sub S UV is a cut metric. And these coefficients, lambda S, so they sum up to 1, and lambda sub S is greater than 0. So suppose we can express our metric in this form. Then we are really in a good shape, because we know that the value of our program is.
Don't we have to normalize distance metric, because so the sum over all pairs of vertices on the right for each S would be greater than 1, and the sum over all the length is 1.
Right. Yeah. We won't be able to do it. That's correct. So I'm saying, so suppose that we have a metric of this form, then we are in a good shape.
Yeah, it's a bit confusing because it doesn't satisfy the condition. This metric cannot satisfy the condition. You put on the sum of all x, all distances is greater than 1. So it's confusing.
Okay. Yeah. Good. Yeah. So our goal will be to convert that metric to a metric of this form in some way.
Okay. Let's in some way ignore this problem for a while.
No. This is right. That metric certainly is not going to be like this. This is a very special metric. But I'm saying that our goal is really to find a metric that can be expressed as a convex combination of metrics. And of course, unfortunately, we won't be able to find a metric like this. So this is a very good metric space. So if a metric can be expressed like this, it's really nice metric, and I just want to see what kind of metric it is, and then we'll try to convert the solution to the linear program to a metric like this. That's what I want to do. In this case, if we could do something like this, so what do we know? So the value of this metric we are interested in is sum of x UV over all edges divided by sum of UV over all pairs x UV. We know that this is equal to sort of LP value of this metric. It's not really, let's call it alpha. So suppose this value is alpha. Then of course, we know that summation of x UV of UV over all edges, maybe here, yeah, is equal to alpha times summation of UV over all pairs x UV. And now we will just use the definition, sort of this equality. So our assumption that x UV can be expressed as a convex combination of cut metrics, and we will get that as summation, maybe changing the summation here, we get summation UV over all edges. Let's put the sum over all sets S in here. So we get lambda S x UV equals.
So you want to prove that the same value is achieved by one of the metric.
Right, exactly. So far I'm just substituting. right? So we have an expression like this, and obviously, so if we just compare term by term, we know that for one s, there exists some s for which this expression is less than alpha times this expression, right? So if we had an inequality in the opposite direction for every s, we wouldn't have inequality in this sum. In other words, we have sort of probabilistic, so here probabilistic distribution of a cut matrix, here distribution of cut matrix, and we know that the expectations are equal, and it means that sometimes expectation on the left hand, so the random variable on the left hand side is less than equal to the random variable on the right hand side. So we get that for some s, the summation over all edges of distances uv is less than alpha times summation of uv over all pairs excess uv. And so that's exactly what we wanted. So this is just one cut, right? So this is a cut metric. It just by the definition corresponds to a real cut, and this is a solution to our problem. So if we could express our metric space as a convex combination of probabilistic distribution of cut metrics, we would find sort of the exact solution to our problem. Of course, the main problem that such metrics are very rare, and we won't be able to find a metric like this. But our goal is to convert our metric space to a metric space like this. And so what are these metrics? These metric spaces are essentially L1 metric spaces. So let me give a sort of a definition of L1 metric space. There are various ways to define it, and one way up to scaling is as following. So we just suppose we have two random variables y1 and y2. So these are just random variables. And we think of this, for the purposes of this talk, we think of these random variables as just defined on a finite domain space, on the finite probabilistic space. So the L1 distance between these random variables is equal to the expectation of the absolute value y1 minus y2. And so let's say that some a metric space is an L1 metric space if you can express it, if there exist some random variables, let's say we have a space maybe V with and metric space defined on V. So we'll say that this D is a L1 metric space if there exists corresponding y's, y sub u, such that distance between u and v in the original space equal to the L1 distance between yu and yv. In other words, it's expectation of yu minus yv.
We're just looking with the random variables.
Hmm?
Why do is random variables in R or where?
Sorry?
What is the random variables?
With real values.
It's just real values.
Real values, right. So what's the relations between L1 spaces and distribution of cut metrics? So we'll see in a moment that this is essentially the same thing up to scaling. Okay. It's easy to see. So suppose we have some again xuv, which can be expressed as a convex combination of cuts. Then xuv is an L1 space. Okay, so why? Can you see this?
I think because just if we have some coefficients for the cut metric, then we just use them as probabilities in our probability space, and each coordinate is either 0 or 1.
Right, exactly. So we can just use these the same coefficients as in the cut. So these lambda s's as probabilities, and for every cut metric, we will so every cut metric corresponds really to partitioning our graph into pieces, right? So we will assign 0, let's say, to the left cut and 1 to the right cut, and we will get exactly the cut metric. So the absolute value.
Every cut metric is an L1 space.
Right.
You just have 2 points. And then averaging can be made by combining the spaces together.
Okay, is it clear? Right. So if you have a cut metric x sub s uv, so it corresponds to some cut s, and we can define a new random variable y sub s. So y sub s of u is going to be 1 if u belongs to the left part of the cut, so whatever s itself, and let's say 0 if u doesn't belong to the set S, right? And in this case, if you look at two guys u and v, then x sub s uv exactly equal to the absolute value ys of u minus ys sub v. And sort of the probability of this s is going to be exactly this coefficient lambda sub s, as we have in the convex combination. So this guy. Okay. Is it clear? No questions? Now, it turns out that the opposite is also true. So if you have an L1 space, then questions? Feel free to ask questions. So it turns out that the opposite is also true, right? So if you have a convex combination of, if you have an L1 space, some distance duv, then it can be expressed as a convex combination of cuts. Of course, so when we express any metric space as a convex combination, of course, then the maximum distance at least is not going to be more than 1. So there may be some scaling parameter So what we have is that DUV, so they exist lambda s, some family of probabilities such that DUV is equal to sum over s lambda s xs UV, and either we need to put here some coefficient. Let's do it this way here. Equals to some parameter t times this. So there exists a convex combination of cuts, and there exists some parameter t such that this holds. OK, so let's prove it. So our so let's look at DUV. We know that DUV is equal to the expectation of y sub u minus y sub v. And let's look, let's M, capital M, be the maximum value of y sub u, maximum over all u, and sort of maximum overall possible probabilistic outcomes. So it means that y sub u is less than m for every u, almost surely. Now what we will do, we'll define new random variable, so corresponding to cuts.
I just want to check whether I understand what you are doing. So I think what we are doing for one-dimensional, imagine it's embedded in R1.
Right.
Then we make a cut at a random point, and this will be what we need. And
Yeah.
if they are not R1 but several coordinates, we just add things together. Yeah?
Right.
Yeah,
Yep.
Okay.
So what we will do, we'll sample those random variables y's, then pick a random point somewhere. I mean, we would want to take just a random real number. It's not possible, so we will kind of bound those variables. So we know that all y hues take values on the interval from minus m to m. So we'll take a random maybe threshold m. And we'll say that so define new variables, let's say z. Zu is equal to 0 if yu is less than m. Zu is equal to 1 if yu is greater than m, where m is an independent uniformly distributed random variable in minus mm. OK? So now let's look for this ZUs, what do you have? So what's the expected value of ZU minus ZV? So if we fix values of variables yu and yv, but don't fix m, so what's the probability? So this value, of course, zu minus zv, it can be always either 0 or 1, right? Because just zu and zv take values 0 and 1. So it is 1 exactly when zu is not equal to zv, right? So we are interested when this value is 1. This value is 1 is so we have this interval minus m to m, and we know that variables y take values there. So here maybe we have yu, and here we have yv. This is just one sample of variables y. And so these two guys are separated if m, small m, is somewhere in between. And so the probability that we separate yu and yv is exactly equal to the distance between yu and yv. Now it's just one-dimensional distance, right? These real numbers, divided by 2m. So because the length of the whole interval is 2m, so the density of this uniform variable is 1 over 2m. So it is 1 over 2 capital M times yu minus yv. So this is for a fixed value yu and yv. So now we average over random choices of yu and yv, and we get this expression. So the answer is 1 over 2m, and here expected value of yu minus yv. And we know that this expectation yu minus yv, this is just L1 distance between yu and yv. So the whole expression is 1 over 2m L1, so sort of the distance between u and v. So we got what we wanted. So we got the 0, 1 variables, and it's clear that these 0, 1 variables are actually cuts. So every time we pick the threshold m, we partition all our vertices into pieces, right? So with those vertices whose yv value is less than the threshold m, and those whose value is greater than the threshold m, right? So in this picture, we have vertices in here and vertices in here. Okay? Questions?
So when we talk about multidimensional keys, so I haven't noticed when you start talking about L1 space with dimension more than 1.
Right. So there are various ways, right, of thinking of L1 space. So I think of L1 as some distribution of one-dimensional random variables. So those variables are index yu, yv. So let me actually once again tell you what exactly we do, because maybe it's going to be easier. So we have these random variables yu, yv, and now we need to find the distribution of cuts. So to do so, we for every kind of choice of yu and yv, so we sample those random variables yu, yv. We get some values. So essentially what we do, we position every vertex of our graph somewhere on the real line, right, corresponding to those random variables. And we know that, so all of them, let's say, lie in the interval from minus m to plus m, capital M. So now we need somehow to generate a cut. And we do probably the most trivial thing of all. We just pick a random threshold on this interval and cut our interval in that place. So we partition vertices that lie above the threshold m and below the threshold m, right? And we get, because of this, we get two sets. Now, of course, we have a distribution of we get distribution of yu and yv. So this placement to one-dimensional line is really random. So it kind of adds randomness to our distribution of cuts as well. So altogether, we have this two random independent random variables, and the answer, sort of the cut and then depends on both the random choice of the threshold and the random choice of y's. Okay?
Yes, and so
one time for all the graph, or
Right, yeah. So m, the small m, it's the same for all vertices. That's important. It's a good point. So what we do, we sample this vector, right? So we have a joint distribution on this embedding of the graph to a real line. This is what really Y-Hues are about. So we have kind of some random distribution that embeds our graph into line. And we know, so what does it mean that this is L1 distance? That the average distance between two vertices U and V, according to this embedding, equals exactly to the distance DUV. Now, we need to convert it to a distribution of cuts. And to do so, we pick also a random threshold from -m to m and cut the graph according to the threshold. So vertices on the right and vertices on the left. And it turns out here that the expected number of times U and V, the probability that U and V are separated by this cut exactly equal to the, not exactly equal, equal up to this constant factor 1 over, I think it's written that way. Sorry.
But if for some reason you want to take different thresholds for each point, it just doesn't change anything.
No. I think the threshold should be the same. Because here it's, for U and V, right, we,
okay. It's just more an unused randomness.
No, I don't think so. Because then
if we take several random variables, independent variables, equal distributed variables, and they take one of them, then we get the same distribution. Okay.
No, for all okay, maybe we discuss offline.
but it doesn't correspond to any kind of, if we take this m for every edge or for every pair of vertices. So it can happen that according to one m, like these two vertices size different parts, and according to the second m, both vertices are the right part.
Right, yeah. So we'd better take the same m for all of them. Any more questions? Okay, yeah, sorry for any confusion. Okay, no questions. And because of this, we really now want to find an embedding into L1 space. And of course, for L1 spaces, there are various other definitions, but they are all equivalent to this one. Right? So if we can convert our original metric to an L1 metric, then we will express this L1 metric as a convex combination of cut metrics. And we know that one of the cut metrics in this convex combination is good for us. There is also some question of okay, well, right. So this scaling factor, let me just note, the scaling factor, of course, is not very important for us because, as we've seen before in the linear program, we can really rescale XUVs, and that won't change the objective function. So now let's go to Bourgain theorem, and the Bourgain theorem says that any metric space it can be embedded, and I'll tell you what it means, embedded into L1 with distortion capital D of order of log n, where n is the number of vertices. And so I won't talk about it, but in general, it holds as well for other metric spaces like L2, and the proof is the same, exactly the same. So sort of for every metric space XUV, they exist L1 metric space. Let's say YU sort of, or maybe L1 metric space DUV such that XUV is less than DUV.
But does it say something about how difficult it is to find this embedding?
Right. Yeah, it can be done efficiently. This can be done efficiently. Okay. And note that this distortion D can put either on the left part, 1 over D, we can put as well, it's here on the right part because we can scale all the metrics. So more generally, we could have here 1 over A put here and B put here, and we require that the product of AB is less than D. You can always rescale metric spaces. But for simplicity, let me write it like this. So this embedding is actually a Fréchet embedding.
There is no S in Fréchet, it's French.
Like this, right? OK. Actually checked somewhere. So it means that there is
I'm not sure.
There is a lot of literature with this type. No, I'm pretty sure that you are right. OK, Fréchet embeddings. And so what is a Fréchet embeddings? And not all embeddings are Fréchet embeddings. But this is some nice property. So suppose we can find some distribution. So Z is a random subset of the set of our vertices V. And Z is not going to be uniform. It's some special distribution, which is important for us. But it is some random subset of V, and it is called zero set. Then to define Fréchet embedding, so Y U of Y of U. So for every I'm sorry. So the random variable Y sub U is going to be the distance we denoted before X from U to the zero set Z. In other words, so what's the distance to the set? This is the minimum distance from U to some point Z in the set capital Z, right?
So the dimension of this image space will be just a number of subsets.
So it doesn't mean that every set, so what again?
Yes.
So but potentially we have
a very large dimension.
Large dimension, right? So what do we do exactly? So we have our graph G, right? This is a set of really vertices. We don't care about edges anymore. So really V. We sample some set Z. And the way we sample it, I'll tell you later. So it's not related to Fréchet embeddings as is. So we take Z. It's a random set. And for this random choice of Z, we defined variables Y sub U. And Y sub U is just equal to the distance between this vertex U and Z. So we take the closest guy, so there may be many vertices in Z. We take the closest vertex and look at this distance from Z to U. Particularly if U belongs to the set Z, then of course the distance from from Z to U is equal to 0. And because of this, y sub u is equal to 0. Okay. Now we need to see how this embedding changes our distances. So we have this metric space XUV, and now we define new metric space. DUV is defined by the L1 norm of YU minus YV, right? So DUV. So what can we say about these distances? And the important thing is that DUV is always going to be less than or equal to XUV. So this is a common property. This is maybe, let's call it theorem.
And again, this set is chosen 1 for
Sorry?
And again, this set is 1 for all graphs.
No, set is random.
A set is random. It's the same for all graph, for all vertices U. We pick one. So what we do, we pick the set, right? It's random, so potentially there are many options. There is some distribution of it, and then for all vertices we define that y sub u. That depends on the same z exactly.
So these property variables are not independent.
YUs obviously are not here independent, correct. Here. So it's important that in our distributions, all this embedding of various vertices are not independent at all. So they're dependent. So who can see why is the distance between U and V? If we define this Fréchet embedding is always less than the original distance between U and V.
In this direction, I think it seems clear. What is not clear, how you can get the upper bound.
Yeah, the other bound is obviously depends on specific way we pick Z. So in general, we can't say anything meaningful about the other direction for arbitrary Fréchet embedding. But this direction, this inequality always holds. Anybody else sees why? Anybody else wants to explain it? Okay, so let's see if you have two vertices U and V, then X UV DUV is equal to the expectation of YU minus YV. And let's look at just one YU sort of minus YV. So this is expectation over distance from U to the random 0 set minus X V to this 0 set. And now we just use the triangle inequality. And we get that this is less than just expectation of DUV, which is sorry, expectation of x uv, which is just x uv, right? So the most important thing, of course, why the inequality in the opposite direction holds. To do so, we need to design Z in some special way, and that's what the Bourgain embedding does. So let's for Bourgain embeddings, let's pick first some probability scale. So we'll take t from 1 to log n. And maybe for simplicity, let's just assume that n is a power of 2. It's not really important, but to avoid some rounding issues. So t is random. And then let's pick every vertex v in set z with probability 1 over 2 to the t. Okay. So in some sets, in the first set, we will pick vertices with probability 1/2, and in the last set, we'll pick vertices with probability 1 over n. So depending on the t. And this exactly defines our random set Z.
T is uniform and true.
T is uniform. It's uniformly right. It's uniformly distributed in this set, and it has log n choices. Now we really need to show that now that this distance yu minus yv is greater than some distortion xuv, right? So we know that we already seen because of the Fichet embedding, duv can be large, can be greater than the original distance, but we now need to show that it's not too small. Let's see. So how to bound this expectation? So let's look at yu minus yv. How can we write it? We can rewrite it in some funny way. It's interval from 0 to infinity. So let me draw a picture. So yu and yv in our case are some non-negative numbers, right? Distances to the set Z. So we have somewhere yu and somewhere yv. I want to first write it like this. So it's the integral from 0 to infinity, and I'll get the indicator variable of my variable x my variable? Maybe small y, belonging to the interval between yu and yv. So we don't really know whether yu is greater than yv. So I'll treat this interval as no matter which value is greater as the interval between these two values, and I have dy, right? So far, what we get that this I, this is here. So this is just indicator variable. Maybe I don't know what's the one. Right. So here it's 1, and here is 0, and here is 0. So far it's trivial statement. So we have this integral, and we have 1 in the interval between yu and yv, so it's contribution 1, and 0 otherwise, right? So obviously the absolute value yu minus yv equals to that expression. So and now we need to
change the order.
No, we are not going to change the order. In some sense, maybe we already did. So now we actually recall what's the definition of the set of yu and yv was, right? So essentially, it's integral from 0 to infinity. And what does it mean? Let me write what it means that y belongs to this interval. It means that y is less than yv and greater than yu, or possibly the other way around. Y is between yv and yu. So let's go back to the definition. So what was yu? Yu was the distance from u to this random set z. So what does it mean that the distance between what does it mean that, let's say, what does this condition mean? That yu is less than y. It really means that if we take a ball of radius y, around the vertex u, there is some vertex from the 0 set, right? That's the only condition. Is it clear?
Here we suppose that yv is greater than yu, right?
Right. So we'll do both cases, but I'm just saying. So let's say we look at this condition, right? Yu is less than y. So we want to somehow write it in terms of our 0 set. And this expression really, this is the same as saying that if you look at the ball of radius, ball in this metric space x around u of radius y, that this ball contains some vertices from z, right? This is non-empty. And what does the other expression mean? What does it mean that y is less than yv? It means that this ball of radius y around u doesn't contain any vertices, right? If that ball around u of radius y contains some vertices from z, so that z would be a witness that the distance between the set z and u is less than y, right? So here is the picture. We have this graph V again. We have a u. Here is a ball of radius, maybe of radius u in this metric space, of radius y. So if you have some z from our set, 0 set z, then of course the distance from u to the 0 set is less than y. If you have no such z's in the ball, so this is a ball, then of course the distance is greater than y. Okay? And ball in this metric space X, U, Vy intersected with Z equals to empty space. So this event happens, or symmetric event happens. So indicator variable of the event ball right. And now we need to actually lower bound this integral. So let's actually lower bound so we can change this integration from 0 to infinity to 0 to half of the distance of uv in the original metric space, xuv over 2. And here we have the same expression as above. So let's pick some y and we'll try to estimate the probability of these events, right? So let me draw a picture again. So what kind of events we want to estimate the probability of? So here is a set V. Here we have vertex U. Here we have vertex V. And we pick some y. Let's fix some y in the limits of the integration here. So it's between 0 and xu v over 2. And we look at the ball of radius y in here. We look at the ball of radius y around u, around v. These balls do not intersect, just because we chose y to be less than xuv over 2. Okay? And we really ask, what's the probability that one of the balls contains at least one point in the zero set, and the other ball doesn't contain any points from the zero set? Okay? So our conditions in integration are symmetric. For a fixed y, one of the balls contains more vertices than the other. So let's say this ball contains n1 vertices, and this ball contains n2 vertices, and let's say that maybe n1 is greater than or equal to n2 without loss of generality. So then we can pick the scale t, like t0, which is approximately equal to log 2 n2. And what we get is that, first of all, we now estimate the probability that there is at least one point in this ball, in the ball around, so there is at least one point z in the ball around u, and there are no points in z in the ball around v. Okay? So this probability 1 over log n, we have that the random t, which we chose for the 0 set, right? T was the scale from 1 to log n is equal to T0. And conditioning on T being equal to T0, let's see what the probability that we have no points in this right ball around V and 1 point around U. So these events are independent, right? Because we pick all vertices independently in the set with probability 1 over 2 to the power of T. And these balls are disjoint. They do not intersect. So the events are disjoint. And obviously, so the probability we are picking every point is equal then, because T is equal to T0, is 2 to the power of minus T0, which is approximately 1 over N2. And so, of course, if we pick all points with probability roughly 1 over N2, then there is a constant probability that there will be no points in the right ball. So if it was exactly 1 over N2, we would get that the probability that there are no points is 1 minus 1 over N2 to the power of N2, right? Because for every point, the probability that we don't pick it in the 0 set, for every point everywhere, is 1 minus 1 over N2, and we have N2 points in that ball for which we make the choices independently, so this probability is roughly 1 over E. Now, the ball on the left contains more points than the ball on the right. And because of the constant probability as well, the probability approximately 1 minus 1 over E if this ball was of the same size. Since it's bigger, this probability can only be bigger. It contains at least 1 point, right? And because of this, again, with some constant probability, the ball on the left contains at least 1 point. The ball on the right contains no points. This is, of course, conditional on this random parameter T was equal to T0. So the probability of that event is 1 over log n. And so this is what we really plug in this integral. So what we get, continuing that integral, maybe integral from 0 to x uv over 2. And here we get some constant because of these computations, and log n, because that's 1 over log n is a probability that t is equal to t0, and here we have dt. And this is x uv over 2 times, c over log n. And that's what we wanted to prove. And so, any questions?
But still, the dimension is extremely high.
The dimension is extremely high, I agree.
Yeah, but
The dimension of the number of random sets is very large, I agree. But it's clear that this algorithm is efficient, so we can run it efficiently. Right? We can pick random t, that's easy, and then every vertex pick with probability 1 over 2t.
So could you say more about the dimension? So what is it? I mean, I just don't remember.
No, not the dimension, right? So as is here, the number of these sets can be exponential. So the distribution is supported on the exponential number of sets. And this sort of may be a problem, as Sasha mentioned, for, if you want our algorithm to be efficient. Mm-hmm. And so there is probably a break now or something. We can make a short break and then continue. Sort of okay, you have some time to think about questions about this proof, because everything else is sort of simpler, and okay, I'll talk about dimensions a little bit.